What's Gucci, everybody? It's been a long time since I've said that, but today I want to make a video on the proofs of sorting. So in my other videos, I've shown you guys algorithms which have a big O of n squared and n log n. But what I want to show you guys is that there is actually a proof that no sorting algorithm can be bigger than log n, or better than n log n, which I'll show you. So remember, such algorithms like quicksort and merge sort are n log n time. So here is about how the proof goes. First, to understand the proof, we have to draw some kind of tree structure. So let's say we have something called x, y. We have kind of a tree here, and we have three elements. We have x, y, and z, and we want to sort x, y, and z. And think of them as, it could be an array, so we have positions 1, 0, 1, and 2. 0, 1, 2, you don't really have to worry about that. But let's say I want to sort these. So first of all, just to point this out, how many combinations how many places can I put in x, y, and z where the order matters? So a different order is a different combination, or a different permutation. So if you didn't know, that the way you do that is it's 3 factorial. It's the number of elements factorial determines how many different orders you can make with the numbers. So 3 factorial, if you didn't know, 3 factorial is 3 times 2 times 1. It just goes down. So that equals 6. So there's 6 different combinations of x, y, and z that you can make. And so let's say I wanted to make a tree, and so let's say I drew that kind of the way to get the 6 numbers in a tree structure. So let's say, first of all, if I have x, y, z, I ask myself if I could possibly sort these elements. Now, for instance, the first thing I'm going to do is I'm going to ask, so I want to sort these elements, so order does matter to me, and so now I'm going to ask myself questions to sort them. So first of all, I'm just going to ask myself a question to sort them. I'm going to say, is x greater than y? Well, here's the thing is, so in different scenarios, x could be greater than y, or y could be greater than x. So that's why this is going to be drawn in a tree structure, because 2 decisions have to be made. So if x is greater than y, this decision is going to happen, and if this is not true, this decision is going to happen. So let's say that x is greater than y. So if x is greater than y, then we know that y must be behind x. So I believe, so for that scenario, there will be 3 combinations, I believe. Z, and then there should be y, z, x. So those are the 3 combinations, right? If you know that x is greater than y, then that is the case. But also, if it's no, then you know, for instance, that y is greater than or equal to x. You can reverse the symbols. So what we're going to do now is we're going to say y is greater. So if y is greater, it's going to be z x y, x z y, and then y x z, I believe. So that's pretty cool, right? So now we're going to go down here, and sorry, my Dropbox is updating, and we're going to go down here, and then we're going to see the other decisions we made, because we want to end up with we want to make a tree to explain every sorted situation. So what I can do here is, up here I can then ask here is, maybe up here I can ask, is x greater than z? And then I can draw a tree based on that. So if x is greater than z, then I know, so for instance, if x is greater than z and that's no, then I know, for instance, because I've gone down into this tree, I know that, for instance, x is greater than y and x is bigger than z. So, for instance, if I know that, then I can say for sure that I can say that if it's no, z is the greatest element, because I know, for instance, that x in the left subtree is greater than y, and then if it's no, I know that z is greater than x. So then I would simply get y x z, which is pretty cool. So if I got that, that'd be pretty awesome. And so that does give me a conclusive answer. But what if the answer was yes? So if x is greater than z, then that leaves me with two choices because I don't know if z is greater than y, which would be my next question. So that would give me, for instance, that would give me a pool of two solutions, which would give me yzx and zyx, because I know x is the biggest element, but I don't know about z and y. So then this route is finished because that is definitely my answer because I somehow managed to organize them in asking the two right questions. But because two things happen to be right. So now I'm going to ask myself, like I said, is z less than y? And if z is less than y, then I know, because if it's yes, then I know the combination is z, y, x. Well, yes, so I know that. So yes means y is the greatest, so then z is the lowest element. And if no, then I know it's x, z, y. So that's how I went down the tree on that cycle, on the right subpath. So now we kind of do the similar thing with no. I'll kind of try to expand it over here, and you see. And so what do I ask here? I actually ask a different question here instead of is x less than y. What I want to ask here is I want to ask if y is less than z, because I want to compare where y is compared to z. So wow, that kind of looks like a yes. So if it's a yes, then what I'm going to do, if it's a no, I'll just do this case. So if it's a no, then I know that y is greater than z, and I know that x is greater than y. So I know x is the greatest element, y is the second biggest element, and z is the third biggest element. So that is pretty cool. Actually, no, I'm sorry. Then I know the reverse. Then I know that x is the smallest element, y is the medium element, and z is the biggest. I know z is the biggest because I'm saying is. I'm sorry, guys. I wrote down my example wrong. So is z less than y? So then this will tell me. So now I know that. So since it's no, I know y is greater than x, and then is y greater than z? And if the answer is no, then I know z is the greatest element, and I know y is the second biggest element because I know x is greater than y from the first branch I took. But if I say yes, then I only know that, for instance, I only know y is greater than z, and I know that x is greater than y. So my possible combinations are x, z, y, and z, x, y. And so now I have z, x, y, and now I can ask myself, is z less than x? And if z is less than x, then I do know, then I have these two branches, the yes and no branch. So if those are true, then I know I can say z, x, y, because I know x is greater than z, and then I know that y is greater than z, and I know that x is less than y. And then if I say no, I can just swip the z and x, because I know that y is the biggest element because I know from going down that y is greater than z, and I know that y from the first branch, y is bigger than x. So that means y is bigger than x and y is bigger than z. So I know that y is the biggest element in this subtree, and then so I just need to figure out between is x greater than z. So as you can see, that gives me x, z, y. Now that's pretty cool. Now, taking this back for a second, I'd like to point out my poorly drawn photos of all of these. And here I've got X, Z, Y, X. I've got 3 branches here. Or I mean 6 branches. I end up with 6 leaf branches, what they're called if you've studied trees before. So I've got 6 branches. And I'd like to point out to you that I had 6 total combinations I could arrange these letters into. So that's pretty convenient, that's pretty cool. So all my leaf nodes ended up being one of the combinations that I could possibly have arranged this tree into. And that is going to help us with our proof. So another thing I want to show you guys is that if I have a full binary tree, a tree with n nodes in a binary tree must require log n plus 1 levels. A tree with that many nodes must require n plus 1 log n plus 1 levels. And you know that because, let's say for instance, and it's log base 2, sorry, I don't want to defer anyone. If I have a regular binary tree with say 4 elements, log 2 of 4, I believe, is going to be 2. Is going to be 2. So what I want to, so that does take 2 trees, but then I want to I'm sorry, it requires at least log 2, at least log n 2 levels. So this proof here is like, so if I have a full binary, if I have this complete tree here, which is as full as it could be for only having 2 levels, then I have log n plus 1, I have 3 with plus 1, which is 4, and then it has 2 levels, so 4 log 2 is going to give me 2. So that's pretty cool. And as you can see here, I had 6 combinations, right? Well, I used 3 elements, which is a total thing of 3 factorial. So I had 6 combinations, or 3 factorial, and if I had 4 elements, it would be 4 factorial. And so basically, I know that at the lowest level, at a minimum, I'm going to have log n factorial levels. That's pretty cool, right? I know I can say I have log n factorial levels because I know that my n, the number of leaves, will always be my combinations, and I'm going to have how many elements I have factorial leaves. And because of that I'm going to be able to, again, make another kind of math. And since we have this log n factorial, we can use something called Stirling's approximation, which I'm not going to go deep into. You can Google it if you want. Stirling. Oh my god, that looks very tiny. Stirling's approximation. And what that says is essentially log of n factorial is equal to n log n, which is our proof. So what we're saying here is that you cannot have a tree we can conclude that any tree must have n log n nodes deep. So it must be a minimum of n log n nodes deep. It is possible that a tree could be unbalanced. So we saw a tree that's perfectly balanced. But it's possible that a tree could be very deep and, have all these nodes here and then just have a few here and then keep going down here and down and down. And it's possible that's true, but it must have at least n log n nodes. So all of these nodes would kind of account for the n log n. So with comparison-based sorting algorithms, that is always the case, and the way to prove that there will always be n log n. There is no better case than n log n, because you must have that many nodes deep in your decision tree to be able to look at all the possible combinations to sort something. Because if you don't look at all those possible combinations, then you truly don't know if it's sorted, or do at least that minimum number of comparisons in the tree. You at least don't know it's sorted. Well, guys, thank you, and I hope you enjoyed this tutorial. It's been very long, and I hope you guys have a great day.